Welcome to AP Chemistry, and in these series of videos I'm going to break down each section of the AP Chemistry exam and work questions similar to those on the College Board. So section 1.1 of the AP Chemistry exam talks about moles and a molar mass. And before we can talk about what a mole is, we need to have this idea of what an atom is. And an atom is going to be the smallest unit of matter that is going to retain all of its chemical properties of a particular element. And so atoms have basically three subatomic particles, and those particles are protons, neutrons, and electrons. And the number of protons that are in one atom are going to determine what that atom is. And so if you pull up a periodic table, you can see that we have helium right here, and this 2 right here for helium, that represents the number of protons in one atom of helium. So if we have a lot of atoms that all have 2 protons, that's going to make up the element helium. And so we can see here we have a 1, a 2, a 3. All these numbers, those represent the number of protons that are in one atom of that particular element. And all of these numbers are called the atomic number. And so what we're going to do is we're going to break down each subatomic particle that is in one of these atoms. And so what we'll do is we'll list this out. We'll put protons here. And if we change the proton number, we're going to change what that atom is. So the number of protons, that's going to define the atom. So we'll put it defines the atom. And we'll build an atom over here. And let's say we're going to build helium. Helium's got 2 protons. So I'm going to put a proton here. I'll put a P with the plus. And we'll circle that. There's a 1 proton. And then here's another P with the plus. And here's my other proton. So this would represent helium. The other subatomic particle is going to be electrons. So I'll write down electrons over here. And what electrons do is those are going to determine the charge of my atom. And so I'll put that it's going to determines the charge. And so electrons have a negative charge, a -1 charge, and protons have a +1 charge. So let's say we want this atom to be neutral. We don't want to have an overall charge of anything. If I have 2 protons in here, I'm going to need 2 electrons to cancel out these two protons. And so what electrons do is those go around the 2 protons. They'll orbit around kind of like this. So I'll put this dotted line down as the path that they go in. And so this electron and this proton will cancel out, and then this electron and this proton will cancel out, and then the charge overall would be neutral. If I add another electron to this atom, it's going to make this atom have a negative charge. And if I remove an electron, it's going to cause this to have a positive charge. So let's write that down. That if we remove an electron, what that ends up doing is that's going to make this have a positive charge. So this will be He with a plus charge like this, right? Because if I remove this electron, this one would cancel out with this, and then I would have this one left over, and that would be a positive 1 charge. But if I were to add an electron, we'll put add here. We add an electron. What that does is it would be He, and it would have a negative charge. So if I add an electron in here, I would have 1, 2, 3 electrons, and then I would have 1, 2 protons. And so I would have 1 more electron than of protons. So if I add an electron, I'm making my atom more negative. Like if I remove a proton, however, I would change the entire atom altogether. So let's say I remove a proton like this. Well, what that does is that's going to make this going to be hydrogen, because hydrogen has 1 proton. All right, if I remove this, I have 1 proton. Go to the periodic table. That's going to be hydrogen. Let's say I add a proton. So we'll add a proton. If I'm going to add a proton, that would be lithium. So this would be lithium. The other subatomic particle is going to be neutrons. So we'll put neutrons down here. And what neutrons do is those will determine if my atom, what kind of isotope I'm going to have. So I'll put that it's going to determine, it determines the isotope. And we'll talk more about those in a second. But what an isotope is that's going to affect the mass of this atom, because neutrons are in the middle along with the protons, and in the middle of an atom, that's where most of the mass is. Electrons are very small in comparison to the protons and the neutrons. The protons and neutrons have about close to the same mass. And so if I add or remove this neutron, it's not going to change the element, because that's going to, because the element will still have the same number of protons. But what this does do is it changes the atomic mass of that atom. So we'll say that if we add or remove a neutron, what that does is it will change something called the mass number. So I'll put that the mass number will change. The mass number will either increase or decrease. And the mass number is basically going to be the number of protons plus the number of neutrons. So that's a good equation to write down. The mass number, what that equals is going to be the protons plus the number of neutrons. And this mass number will always be a whole number. So I'll put it's always a whole number. And the reason why is because it represents the number of things. It represents a number of protons, a number of neutrons. Protons and neutrons, you'll never have half of one or a fraction of one. It will always either be you either have one or you don't. And so the mass number is always going to be a whole number. So if you see a decimal, you know that cannot be a mass number. And so what we would do for this, if we want to write this out, we would say that we have two protons here. That would be He, because it has two protons. And then we put a dash here, and we would put the mass number. And the mass number would be, we have 1, 2, 3, 4 subatomic particles in the center are called the nucleus. So we would put He, and we put a 4 to describe what isotope this is of helium. It is helium with the mass number of 4. Another way that we could write this would be like this. If we said that we have He here, and I put a 2 here, and I put a 4 up here. And this 2 right here, this would represent the number of protons, also sometimes called the Z number. So this right here is going to be my Z number, and this 4 over here would be my mass number, sometimes also called an A number. So here's my Z number there, and then here's my A number there. And a lot of times you'll see it written like this whenever you want to describe a nuclear reaction. When you want to describe reactions where maybe the number of protons or the mass number might change, you would write it like this. So we're going to write this. So you write it like this for a nuclear reaction, for nuclear reactions. You'll see it oftentimes like this. And so let's try a practice problem using this information. So here is practice question number 1. And it says it wants to determine the element, charge, and mass number of an element that has 7 protons, 8 neutrons, and 10 electrons. Well, if we're trying to figure out what that element is, what we need to do is we need to look at the number of protons, because that determines what the element is. So we'll go to the periodic table that we have right here. It's 7. So that must mean that this is going to be the element nitrogen. So let's put that down, that this is going to be nitrogen. So it's going to be an N. So that takes care of that one. And then we want to figure out what's the charge going to be. Well, the charge, to figure that out, you would look at the protons and look at the electrons. And whichever one is in excess the one that's left over in excess, that's going to determine what the charge is. And so I have more electrons than I do a proton. So I know my charge has to be negative because electrons are negative. So when I subtract these two, I would get a -3. So the charge of nitrogen would be 3 negative, and you put that at the top like that. The next one that we need to do is figure out what the mass number would be. And the mass number just comes from taking the number of protons plus the number of neutrons, and we add those up. So when we add 7 plus 8, we get 15. So this would have a mass number. We could say a mass number equal to 15. And so that's practice question number 1. Let's try an example question now. Example question number 1. So it says this. So it says it wants to determine the number of protons, neutrons, and electrons in this Ca, and it's got a 20 on the bottom, 41 up top, and it's a 2+ charge. And so take some time to figure out what you think this would be for protons, neutrons, and electrons. So the number of protons in Ca, you could go to the periodic table to figure that out, but if you look right here, it's telling you this number right here is the Z number. And so that represents the number of protons. So the number of protons for this problem would be 20. And then there's a 41 up here, and so that's going to be the mass number. That's the mass number. And the mass number represents the number of protons plus the number of neutrons. So if the number of protons plus neutrons is 41, and we just want the neutrons, what we would do is we would do 41 minus 20, and you would get 21. So the number of neutrons here is going to be 21. And now to get the number of electrons, what we would do is you would look at the overall charge, and you see that you got a 2+ charge here. So I need to have 2 more protons than I do electrons. And you can't change the number of protons because that's going to change the element. So the number of protons is fixed in this way. So we have 20 protons, and we want to have 2 more of those than of electrons. So that means I'm going to have 18 electrons. So the number of electrons is going to be 18. So now let's move on to talking about isotopes. So what isotopes are different versions of a particular atom. So let's say I have something like lithium, and I'll put -6 here, and I'll have lithium over here, and I'll put -7. So this 6 and 7, those represent the mass numbers. And these are both lithium, which means both of these have 3 protons. So I'll put 3 protons there and 3 protons there. And if this is a mass number of 6 and I have 3 protons, it means that I must have 3 neutrons over here, because this number plus this number has to equal this number there. And if I have 3 protons here and the mass number is 7, that must mean that I have 4 neutrons over here. And so the main difference between these two are the atomic masses of both of them. And so the mass of one proton is going to be about 1.007 atomic mass units. And the mass of one neutron is going to be 1.009 atomic mass units. And so what we'll do is we'll figure out the atomic masses of each of these. And so let's take that we got 3 protons, and the mass of just one proton is 1.007. And if we multiply those together, we'll get 3.021. And if we take the number of neutrons, we have 3 there. And the mass of one neutron is going to be 1.009. And multiplying those two together, we get 3.027. And so we add these two numbers up, and we get the atomic mass of lithium-6, which is 6.048 atomic mass units. And now let's figure out what the mass of Li7 would be. So I still have 3 protons, and one proton is 1.007, and that's going to be 3.021. And I have 4 neutrons this time, so that's 4 times 1.009, which is going to be 4.036. and we'll add these two numbers up and we get 7.057. And so these numbers right here and right here, those represent the atomic masses of each of those. And the problem comes up where we don't know which number to put on the periodic table. So what we do is we'll get an average of both of these, but we cannot just take these two numbers here and add them up and then divide by 2. And the reason why is because lithium-7 is more abundant than of this one. So this one's going to be about 92.41%. And this one over here is going to be about 7.59%. And so we have these two different versions of lithium. And if we were to scoop up some lithium, 92.41% of it would have this atomic mass units, would have this atomic mass. So I'll put AMUs here, and we'll put AMUs over here. And what we want to do is we want to get an average. So what we do to get an average of this is I'm going to take this number here and convert it to a decimal and multiply it by that number there. So we're going to do 6.048 times 0.0759, and we're going to add that one to, we have 7.057 times 0.9241, and when we do this out, we're going to get 0.459 plus 6.521, and we get 6.98. And this would be AMUs here, and this is going to be the average atomic mass of lithium. So what I'll put is the average. I'll put average atomic mass. So if you go to the periodic table, this would be the number that you're going to find, or something, pretty close to that. And so lithium would kind of look like this. We would have Li, and on the periodic table you have a 3 up top, and then we would get this 6.98 on the bottom. And that's what this bottom number means. This bottom number is the average atomic mass. It's a very common mistake for students to mix up this number with the mass number. If you ever see a decimal, that's going to tell you the average atomic mass of all the isotopes of that particular element. And so now let's talk about how and why we want to take this information and find a mole. So in chemistry, we'll talk a lot about chemical reactions, and chemical reactions involve a reactant on the left side, then there's an arrow, and then there's products on the right side. And this arrow means that the reactants are going to form products. And so a typical reaction might look something like this. That way you have something like H2O2, and then there's the arrow, and it's going to make something like H2 plus O2. And so this is hydrogen peroxide decomposing into these two chemicals. And so we might be doing something like this, that we got 10 grams of this chemical, and we want to figure out how many grams over here and how many grams over here that we're going to end up making. And so to solve this problem, you don't want to think about this in terms of how many grams of this chemical you have to grams of this chemical. What you want to do instead is think about how many individual molecules you have of this one to form molecules over here. And so a good analogy that I could think of would be that if we have two feathers, and what we want to do is we want to combine the two feathers maybe to like a brick, so it can be some type of like arts and crafts project. And so here is the brick, and we're gonna combine the two, and we're gonna make a feather brick arts and crafts project. And so it kind of looks like this. And let's say we have 10 grams of each of these. I have 10 grams here, and I have 10 grams here, and I'm going to figure out how many grams over here am I going to end up making. Well, you wouldn't think about this in terms of how many grams of feathers you have. You would think about this in terms of how many individual feathers you have to combine to this this brick over here, how many individual bricks you have. But it's very practical to think about this in terms of how many grams you have if you want it to have a lot of feathers, maybe like a couple thousand feathers. And what you would do is you essentially would count the number of feathers you have by weighing them. And that's the same kind of idea up here that you're going to do. You're going to count how many individual molecules of this chemical you have by weighing them. And so what you want to do is you want to convert from grams to something called a mole. And a mole is basically going to be the number of molecules or atoms you have of a particular chemical. And so you would go from grams of a chemical to moles of that same chemical, and then you would go from moles of that chemical to moles of the chemical that you want, and then you can go from moles of this new chemical to the grams, and this is how you would solve this problem. So you would go from grams of this right here to moles of this, and then you can go to moles of whatever chemical that you want to find, and then you can go to grams. So you would follow this path like this. And what you don't want to do, though, is you don't want to just go straight from grams to grams like this. This would be the wrong way to solve this problem. And so what we need to do is we need to figure out what is the difference between a molecule versus an atom. And so let's work an example question where we have something like this. We have Ca, and then we have CaOH2, and then we have something like O2 like this. And so let's say we're given grams of this Ca. Well, what we would do is you would go from grams to moles, and then if we want, we can go from moles to something like atoms. And that would tell us how many atoms of Ca that we have. But what if we're given grams of something like this chemical? We have grams here, and if we go from grams to moles like this, but this time we're not going to be in atoms, we're going to be in molecules instead. And the reason why we're going to be in molecules is because this chemical right here, it's got two different atoms being, or at least two different atoms being put together to form this. It's got more than two. So we would be in molecules this time. But we could go to atoms, but we would have to pick which one we want. So we could either go to atoms of Ca, or we could go to atoms of oxygen, or we could go to atoms of hydrogen. We have to pick which one we want. And so if we have grams of something like O2 like this, we would still go from grams to moles just like before. And this time we would go to moles to molecules, because this O2 is a molecule of oxygen, not an atom of it. And the reason why is because there are two oxygen atoms that make up one molecule of this. And so we could still technically go to atoms if we want, but we would have to first go through molecules. And so what we're going to do now is talk about how we can go from grams to moles. And the equation to go from something like a gram to a mole is going to be this equation over here. And as a mole is going to be equal to the amount in grams divided by the molar mass. And a molar mass, that just comes from the periodic table. And so what we want to do now is we're going to work through some questions where we're just going to go ahead and find the molar mass, and that'll be useful to finding out number of moles, and it'll help us do questions kind of like this. So let's say that we have something like this. We have something like NaCl, and we want to find the molar mass of NaCl. Well, in one NaCl, I have one Na, because there's a 1 right there in front of the Na. There's no number there, so it's going to be a 1. And so we're going to say the Na, we have one of those. And the Cl, we're going to have one of those as well, because there's a 1 in front right there. And so what we'll do now is we'll go to a periodic table, and we're going to look up what is Na and then what is Cl. What's the what's the number of the mass of that's composed of the protons and neutrons that are making up this mass. And so we go over here and we see the average atomic mass of Na is going to be, it says 22.9. We'll just go ahead and round that to 23. So we're going to say that we have 1 Na, and we'll multiply that by 23. And then we're going to add that to the next one. We have 1 Cl, and we'll multiply that by the mass of Cl, and Cl is going to be over here. And it says 35.4. We're just going to go around that to 35. And so when we do this out, 23 plus 35, that's going to be 58. And so the molar mass of NaCl is going to be 58, and we can put AMUs. Or you could also say it's going to be a gram per mole. And so let's try this again with one that's got parentheses. And so if it's got parentheses, we'll do something kind of like this. Let's say we got something like, we'll do Ba, and then we'll put parentheses, OH, and then a 2 right here. So we're going to have to count up all the different atoms in this chemical. And that's going to be that we got a Ba. So we'll see how many Bas do we have. Ba, we have, let's see, there's a 1 right here. So that means in this one molecule of BaOH2, we have one Ba atom. And so we have 1 there, and then we have oxygen. Now this 2 is going to distribute to this entire thing over here. So we're going to say that we have 2 oxygen atoms for one of these molecules. So oxygen, we have 2 of those. And then this hydrogen over here, we would also have 2 of those, because this 2 will distribute to over there. And so to get the molar mass of this, we would do something like this. We would say, okay, we got 1 Ba, and Ba on the periodic table is going to be right over here. And so that's going to be 137. So we'll do 1 times 137. And then we'll add that to the oxygen. The oxygen is right here. We have 2 of those. So we'll do 2 times the oxygen is going to be here. That's going to be 15.9. We'll round that to 16. And then we'll add that to the next one is hydrogen, which is over here. And we want to use that number right there on the bottom, and we'll go ahead and round that. So we got 2 of those times 1. And so when we add all this up, that's going to be 171. So this is 171 atomic mass units, or we could call it a gram per mole. The units are exactly the same. A gram per mole and an atomic mass units, those mean the same thing. So that's how you're going to find a molar mass. Let's go ahead and try to do some more of these problems. We'll do like practice question number 2. So for practice question number 2, what you want to do is you want to count each individual atom in that chemical, and then you want to go to the periodic table and you want to see what the average atomic mass is for that particular atom. So for example, we have CH4 here. So we have C, and then there's no number in front of that C, which means you're going to have 1 atom of carbon in there. So you want to do 1 carbon, and then times, you want to go to the periodic table. So if we go to the periodic table and look at carbon, it's going to be right here, and that's going to be this 12 right there. So then what you want to do is you want to go to this carbon and you want to put a 12 down, and then you want to add that to, you have 4 hydrogens right here. So you want to do 4 times the mass of just 1 hydrogen. And so what we'll do is we'll go and look at hydrogen, and we'll see that it's going to be right here, and we'll see this number there is 1. So what you want to do is you want to do this 4 over here times 1, and that's going to be 16. And that 16 grams per mole is going to be the molar mass of CH4. For this one, you want to say that you have 1 Ca, so we'll put a 1 down, and then we'll times the Ca. The mass of just one of them will be 40, so you'll put 40 down, and then you want to add that to, now we have 2 of NO2s. So you have, in this molecule, you have NO2, and you have 2 of them. So you have a total of 2 Ns, and N on the periodic table is going to be 14. So you'll have 2 times that 14, and then you want to add that to, you have NO2, and you have 2 of them, which means you're going to have 4 oxygens. And so you want to do 4 times 16. And when you add up all these together, you're going to get a molar mass of 132 grams per mole. And so this is the molar mass of this chemical here. For something like H2O, you want to say you have 2 hydrogens, right? And then you're going to say 2 down like that. The mass of just 1 hydrogen is going to be a 1. And then you're going to add that to the oxygen. There's no number in front of the oxygen, so it's going to be a 1. And so you're going to have 1 oxygen times the mass of that on the periodic table. You're going to put a 16 down. And so this would have a molar mass of 18 grams per mole, or atomic mass units, whatever one you like. And so for this chemical, we have Na2SO4, and then this 10H2O means that that's part of this right here. It's all 1. And so what you could do is say, well, I know the molar mass of H2O is going to be this 18 right here. And so if I have 10 of these, it's going to be this 10 times 18. And so we could say, well, this right here is going to be 18. Now we've got to figure out what the molar mass of this is going to be. So what we'll do is we'll say we have Na, and that's going to be that we have 2 of those. So let's say we got Na, it's going to be, we have 2 of those. We have S right here, and we have 1 of those. And then we have this oxygen here, and we have 4 of those. And then the H2O, we're going to have 18 of those. And so these are the numbers I'm going to use when I want to figure out the molar mass of this chemical here. And so what I'll do is something like this. We'll say we got 2 NAs. The Na on the periodic table is going to be 23. And we'll add that to, we got 1 S on the periodic table. The S is going to be 23. And then we got oxygen. Now it's this oxygen. I know oxygen's over here and here, but we take into account this oxygen when we took into account the water over there. And so we have 4 oxygens. Oxygen is going to be 16. And then we got 18 of these waters. We got 10 of these waters, and the molar mass of that's going to be 18. So when you add all this up, you're going to get 322 grams per mole. So that'd be the molar mass of this chemical here. So let's say that we have grams of some chemical. We could go from grams to moles of that chemical, and then from moles, we could go to either molecules of that chemical, or we could either go to atoms of that chemical. And which one we go to will depend on what the chemical formula is. And so to go from grams to moles, you're going to use this equation. You're going to use the equation that a mole is equal to the amount in grams divided by the molar mass. And then to go from a mole to either a molecule or an atom, you're going to use Avogadro's number. And that is that 1 mole of anything is going to be equal to 6.022 times 10 to the 23rd power. And so let's do a problem where we're using this information. Let's say that we have 432 grams of something like Ag, which is silver, and we want to figure out how many atoms of silver is that. So to go from grams to moles, you're going to have to do this equation right here. And what we're going to do is we're going to take 432 grams and we'll divide that by the molar mass, which is 108 for silver. And so that gives us 4 moles of silver, which is Ag. And so now what we'll do is we'll go from moles over here to atoms, and we'll do Avogadro's number to convert that. So we're going to take that we have 4 moles of Ag, and we'll put that over 1, and then we'll do a dimensional analysis to figure out how many atoms that is. So I'm going to put atoms up here on the top, and I'll put moles right here on the bottom. And then Avogadro's number says that for every 1 mole, we're going to have this number of atoms. So we're going to put 6.022 times 10 to the 23rd power up here. And then we have moles here, and moles here cancels out. And then we'll have 4 times Avogadro's number divided by 1, and that's going to be 2.4 times 10 to the 24th power, and that's going to be atoms of Ag. And so this is how we would find grams to atoms. So now let's try to do practice question number 3. So practice question 3 says that we have grams of some different molecules, and we want to find a certain number of atoms that are within that molecule. So for this first one, we have 1.6 grams of CH4, and we'll have to first go to a mole using a gram to a mole conversion, and we'll do this equation right here. So we're going to say that we have 1.6 grams divided by 16, which is the molar mass of CH4, and that's going to be 0.1 moles of CH4. And so now that we have moles, we can go from moles to molecules, and we'll use Avogadro's number here. And so we're going to say that we have 0.1 moles of CH4, and I'll put that over 1. And then what I'll do is I'll set up my dimensional analysis, where I'm going to put a mole on the bottom, and then I'm going to put molecules up top. And I'm going to say that every 1 mole is going to be 6.022 times 10 to the 23rd power. And now moles here and moles here will cancel out. And when I do that, I'm going to get 6.022 times 10 to the 22nd power. And that's going to be molecules of CH4. And so now that I have molecules of this, I can go to atoms of any one of these that I want, and I'll go to the atoms of carbon right here. And so what I'll do is I'll set up another dimensional analysis, where I'm going to say that I have 6.022 times 10 to the 22nd power, and that's going to be of molecules of CH4, and I'll put that over 1. And what I'll do is I'm going to say that I have, for every 1 molecule of CH4, that's going to be 1 carbon atom. And so now I'm going to have molecules of CH4 and molecules of CH4 cancel out, and I'll be left with carbon atoms. And so what I'll do is I'm going to do Avogadro's number times 1 divided by 1. And so that's going to be 6.022 times 10 to the 22nd power, and that's going to be atoms of carbon. For this next question, we have 396 grams of this chemical right here, and we want to find the number of nitrogen atoms. So what we'll do is we're going to go from grams to moles, and we'll do this equation right here. And so I'm going to say that I have 396 grams divided by the molar mass of this chemical, which is going to be 132, and that's going to be 3 moles of Ca, and we have NO2, and we have 2 of them. And so now what we're going to do is we're going to go from moles to molecules, and I'm going to use Avogadro's number. So I'm going to say that I have 3 moles of Ca, and then I have NO2, and I have 2 of them. I'll put that over 1, and I'm going to use Avogadro's number to say that for every 1 mole of this that I have 6.022 times 10 to the 23rd power, and that's going to be molecules of that chemical. So this time we're going to have moles and moles here cancel out, and we'll have 3 times Avogadro's number, which is going to be 1.8 times 10 to the 24th power, and that's going to be molecules of that chemical. It's CaNO2, and we have 2 of them. And so now what we're going to do is we're going to go from molecules of this chemical to atoms of just the nitrogen. And so we'll put that we have 1.8 times 10 to the 24th power, and that's going to be molecules of CaNO2, and we'll put that over 1. And then we're going to say that we have, for every 1 CaNO2, we're going to have 2 nitrogen atoms. So we have 2 N atoms. And so when we do this, we're going to have that the molecules in here and here will cancel out, and we'll be left with atoms right here. And so what we'll do is this number here times 2 divided by 1. And when we do that, we're going to get 3.6 times 10 to the 24, and that's going to be atoms of N. And so this would be the answer right here. Now let's try example question number 2. In example question 2, it says, which of the following would have the most number of moles in a 1 gram sample? So if each of these compounds only has 1 gram, which one do you think would have the most number of moles? So take some time to think about which one I think that would be. To answer this question, you have to know the equation for a mole. And a mole is going to be equal to the amount in grams divided by the molar mass. And if the amount in grams right here is going to be fixed because each compound has the same number of grams, they each have 1 gram, and you want to make the moles have a high number, then you want to get the molar mass to be a low number. So you want to pick the compound that has the smallest molar mass, and that's going to be LIF, this one. So LIF would be the answer. Now let's try example question number 3. In example question 3, it says, which of the following would have the most number of moles of atoms in a 1 gram sample of each? So if each of these compounds only has 1 gram, which one do you think would have the most number of moles of atoms? So take some time to think about which one you think that would be. To answer this question, you have to know that a mole is going to be equal to the amount in grams divided by the molar mass. And so let's start off with Kf. And Kf says that we have 1 gram, and we'll divide that by 58 because that's the molar mass, and that's going to be equal to 0.017 moles of Kf. And so what we'll do now is we're going to convert this from moles of this molecule to moles of this atom. And so what we're going to do is we're going to say that for every 1 molecule of Kf that we have, we're going to have 2 atoms because Kf has 1 atom of K and 1 atom of F. And so when we do this, we're going to get that we have 0.034 moles of atoms of Kf. And so now let's try MgF2. So we're going to have 1 gram, just like before, and we're going to divide that by 62. And then that's going to be 0.016, and that's going to be moles of MgF2. And so what we'll do now is we'll do a dimensional analysis just like before, and we're going to say that we have, for every 1 molecule of MgF2, that's going to be 3 atoms because we're going to have 2 atoms of F and 1 atom of Mg. So when we do this, we're going to get that we have 0.048, and that's going to be moles of atoms of MgF2. And because this one right here is going to be more, that means that the answer is going to be MgF2. And a mole is just Avogadro's number, which is 6.022 times 10 to the 23rd. So if we want to get the number of atoms, we would just say this number right here times 6.022 times 10 to the 23rd, and that will be the number of atoms that's in MgF2. Now let's move on to section 1.2 and talk about mass spectroscopy. And mass spectroscopy is a technique that's used to determine the relative abundance of different isotopes. And so let's say that we have an isotope of Cu. So let's say we got Cu63 here, and then we got Cu65. And in the sample, we have both of these isotopes. And this technique allows us to see which one would be more abundant, which one would have the higher percentage if we have both of these in a sample. And so what we end up doing is we take the sample of both of these and we're going to put them in here. This is the sample inlet. We're going to stick both of them in here, and then what happens is two things. First, we're going to heat it up, and then we're going to ionize it. So we're going to shoot basically electrons at it. And when we shoot electrons at it, what happens is it knocks an electron off of the sample. So this goes from a Cu, which is going to be neutral, to Cu, which is going to have a positive charge. And the same thing is going to happen to this Cu too. This will be Cu with a positive charge as well. And so now we have these, both Cus, both coppers, well, they have the same number of protons, different number of neutrons, which means they're going to weigh a different amount. So they have different masses. And so what happens is they're both going to go through this slit right here. So this would be Cu65, and then we can have the Cu63 and going in here. So both of these are going to be charged. And what happens now is they're going to go through this magnetic field. And this magnetic field has a positive on one end, and it's going to have a negative on another end. And magnetic fields generate electrical fields. And so what you have here now is you have an electrical field that can be felt by both of these chemicals. And so what happens is when you have these charged chemicals going through this field, there's going to be a force that's going to be felt. And both of them are going to feel the same force, but they're going to be deflected differently. Like they're going to gravitate to one end of the magnet because they're going to have different masses. So it's going to be easier to deflect the lighter one, and it's going to be harder to deflect the heavier one. So this one right here, this one that's lighter, is going to be easier to deflect. So this one would be easy to deflect. And the heavier one would be harder to deflect. This one would be harder. So this is harder to deflect. And so what happens is they're going to deflect differently. So now they go through one of a couple different slits. And after they go through that slit, they're going to go through a detector, and then they go to this computer, and this computer basically reads out how many of them were able to go through a particular slit. And the idea is that because the heavier one won't be as deflected as much, and we know how many of those went through, and we know how much of the lighter one went through, both of them being the same copper, we can get an idea of the different masses of each of them. And so what we'll do now is we'll talk about what this display means and how to determine how to read this data. So here's an example of a mass spectroscopy graph, and let's talk about how we would analyze this graph. So these two lines right here, those represent different isotopes. And this line right here, the isotope has an atomic mass units of 63, and the other isotope over here that has an atomic mass unit of 65. And you might be thinking, well, this 63 right here and this 63 right here, are those the same number? And the answer is no. This number right here is the mass number, and this number right here is the atomic mass units. And the reason why they're so similar is because this number right here, the atomic mass units, that represents the number of protons and neutrons, the masses of those added up. And the atomic mass units for one proton and one neutron is approximately 1. So that's why these numbers are so close. But this number right here is really a decimal. It's just that you couldn't fit the decimal on this graph, so they just put it right here. So it's really, if you were to look this up, this one right here is going to be the atomic mass units. It's going to be 62.93 atomic mass units. And this one over here, the 65, that's going to be 64.92 atomic mass units. And so this one right here would represent the isotope Cu65, and then the line right here would represent the Cu with the mass number of 63. And so what we could do is, if we know the abundances of each of these, then we can figure out what number would go on the periodic table. And so this one right here, we could look at the abundance. Now, it doesn't say it on this graph, but the abundance would be 69.15%. And the percent of this one over here, that would be approximately 30.85%. And so if we know the percent of both of these, and we know the atomic mass units for each of them, we can figure out what number would go on the periodic table. And so what we'll do to figure that out is we'll do 62.93 for the atomic mass units for this one, and then we'll multiply by the percent in decimal form, which would be 0.6915. And then we'll go ahead and add that to the other one, which is going to be the 64.92 times this number right here in decimal form, which would be 0.3085. And for that, we're going to get, let's see, 43.52. And then we're going to add that to the other one, which would be 20.03, and when we add those two numbers up, we get 63.5. And then if we go to the periodic table for Cu, we see that it's this, and this is a number on the periodic table, which is going to be the average. I'll put AVG here. This is the average atomic mass. So let's try to do an example question now. Let's try example question number 4. Example question 4 wants us to determine the element from the mass spectrum graph. So from looking at this graph, see if you can figure out what you think the answer would be. To solve this question, you have to know how to read this graph, and you have to know what each of these lines represents. So these lines represent the different isotopes that are part of the same element. And what's on this axis, the x-axis, is the atomic mass. So this is going to be the atomic mass. And it's not going to be the average. The average atomic mass would be somewhere in between these two. A common mistake is students will confuse this number right here with the mass number. And this is not the mass number. The mass number is the number of protons plus the number of neutrons. And this is telling you the atomic mass, kind of like you can think of that as the weight of the particular isotope. And so what we want to do is we want to go to a periodic table and we want to look and see what atomic mass, the average atomic mass, is between 11 and 10. But because this one right here is larger, we want to find an average that's close to 11 but not quite. So we want to find a number that's going to be in between these two but more over here to this right side. So if we go to the periodic table, we can see that we have looks like boron right here, and that has an average atomic mass of 10.8. And so if we go back to the question, it says that we have C right here, and that's going to be boron, which is going to be the answer.